Good afternoon. This is our presentation of the simulation of atherosclerosis plaques to see the effects of flow in an artery. We are Team 10 made of Alejandra Fierro, Pedro Olvera, and Narciso Martinez. First of all, atherosclerosis is a progressive disease characterized by the tightening or hardening of the arteries caused by the buildup of fats, cholesterol, and other substances in and on the artery walls. Some of the possible causes of the disease are heart attack, stroke, aneurysm, and blood clot. And some of the risk factors are a high cholesterol, high blood pressure, smoking, obesity, etc.
The following parameters were researched in order to understand how does the coronary artery and blood fluid behave under mechanical properties. Also, they were useful for the design in SolidWorks.
In order to generate our experiment, we were given two aortic models. One presented a healthy state, while the other presented a pathological one. Boundary conditions were also established at 0.2 meters over second for velocity and 120 millimeters of mercury for the environmental pressure. Finally, the processing of these models was executed using the SolidWorks program where the flow simulation was conducted. The flow velocity results that we achieved indicate that the pathological vessel presents alterations concerning its flow velocity. This can be observed on the area that varies in diameter, leading to an uneven flow velocity. Although the peak velocity doesn't change radically compared to the healthy vessel, the model offers a clear view on the areas that are affected.
Both pressures are very similar in the healthy and pathological vessel. Healthy one with 125.64 millimeters of mercury and the pathological one with 126.14 as their highest pressures. We can see that the pressure lowers when the diameter of the vessel increases. But when it comes to the final part of the vessel, the carotid bifurcation, is where we can observe the greatest levels of pressure in both vessels.
The shear stress models offer a clear view on how the variation in dimensions and pressure can affect negatively areas of the aorta. Observing the pathological vessel, we can establish that the pathology present generates a considerable amount of shear stress on the midsection of the model, which could lead to the rupture of the wall.
After doing the modeling in SolidWorks, we were able to visualize the specific change that exists mechanically between a healthy artery and an artery with atherosclerosis. We mainly noticed the greatest difference in the pressure that is exerted on the walls of the capillary vessel, being the most important risk. The plaque rupture due to atherosclerosis can put the patient's life at risk and even cause death.
In conclusion, computational fluid dynamics is a unique tool that offers a way to visualize and analyze behavior of anatomical fluids in order to process the information quantitatively. Also, this technology is useful for hemodynamic analysis. It's key to develop an engineering understanding of anatomical fluids pathologies, always having the patient as a priority.